Okay, so um, we already have talked in the last class that heat can do some amount of work, and all the work can be converted to heat. Now, if you're talking about thermodynamic systems, which we usually will be dealing with gases, gas system of gas, let's talk about how a gas does work. We already know that in mechanics, work is defined as if you have a mass or any object and you apply a force F such that it moves on this axis D, which makes an angle theta. We know W is given as F dot D, which also means F d cos theta, where F is the magnitude of force and D is the distance, magnitude of the distance moved. So, in case of gas, we can use the same formula, and let's talk about a simplistic case. Well, so what we have is we have a piston. These are some standard ways of understanding things, and this piston has similar. You see all these pistons in car engines, or actually in engines. This piston actually has an air or gas which has pressure P. The piston has volume V. Now let's say this pressure actually is greater than the pressure outside, so this gas is gonna push this piston upward. And we know, let's say it pushes this piston up. But let's assume this push as small movements, which means that let's say the change of volume goes from V to dV plus V, which means volume is not V anymore, but it has become dV plus V, where dV is a small change, very small change. Now, if this is a very small change, we can sort of approximate that P is gonna stay the same. Well, as a matter of fact, you can also say that P has changed to P minus dP. There's a change, pressure has reduced, but you will see that the contribution from dP is gonna be, it can be ignored. So let's assume that this P, the pressure stays the same, which is P. So we can use the same formula here. If we call A as the area of the piston, we know that force is gonna be P times A, and the let's say the change in height dH is gonna be actually I should write dV equals A is the area of the piston times the change in height of the piston dH. So the small change in dH is going to change the volume, small volume of the gas, and you can see that A is the area, and this guy is moving up with the distance dH. So the volume it has vacated is going to be this. So what is going to be work? So work is going to be F times dH. You know, F is in the upward direction, and H also, or dH is also in the upward direction. So W is going to be PA times dV divided by A, right? This is force, this is distance. So what do we get? We get P times dV. Well, actually work done is going to be small work, because there's a small amount of work done, not a whole lot of work done. So we see that actually dW, or work done by a small work done by a force, is going to be this. Now you know that if you let this happen such that the piston keeps on moving until it reaches the top, such that the pressure inside is same as pressure outside, you know you have to add all these small dW's to calculate the total amount of work done. the way we know the sum is done is we integrate over all the dw's. So this is nothing but p dv, where we actually change our volume from v, let's say initial, to v final. This will become clear in different problems how to calculate this integral, but this is going to be the total w. But let's say if you have cases when p remains constant, you can create a situation when p remains constant. In that case, we know w is going to be p times delta v, where this is change in volume. So the integral is going to assume this form. If p remains constant, you can take the p out. Integral vi to vf is going to be dv. Well, actually delta v, you know, is vf minus vi. So this is a standard formula to calculate the total amount of work done by a system involving gases, because gases usually we'll talk about system containing gases. Okay, we'll talk more in the following class.